All right, now we're going to start on a force on a current carrying wire. So just like we saw in the last section, how a wire with current can exert force on a magnet, by Newton's third law, the opposite's got to be true. If it's putting a force on the magnet is putting a force back on it. So we're going to look at how that works here. So let's say I've got a battery hooked up like this, and I've got two magnets here. First off, we know that magnetic field lines point from north to south, so I'm going to have magnetic field going in this direction right here, or at least right over top of the wire where it's going to be the strongest. And now we're going to upgrade our right-hand rule. Before we were just doing it for a wire, now we're going to use it for any particle, no matter how it's traveling. So as long as it's a positive particle, the right-hand rule works. If it's a negative, you'll use the left-hand rule. But let's figure out how the right-hand rule works. The left-hand rule is just the opposite. So in this one, what you're going to do is you're going to point your index finger in the direction the current is traveling. And remember, since it's a positive particle, that's in the direction of conventional current. So we know the positive side of our battery is on the top, meaning positive current is going like this. So what I'm trying to do in this one right here is find the direction of the force. So first thing I do is point my index finger in the direction of the moving charge, which in this case is our current. Next thing I'm going to do is point my middle finger in the direction of the magnetic field. In this case, the magnetic field is pointing that way. So right now, I've got current is going down, magnetic field is going right. Let's find the direction of our force. So index finger down, middle finger is pointing that way. So now my thumb is going to show where the magnetic field is, or the force of the magnetic field, and it's pointing out. So so the force in this case is going to be outward. If you remember, to show going into the page, you put an X, like you're looking at an arrow that was just fired. There's the fletching. If you have something coming at you, it's this, where you see the tip of the arrow coming at you. A funny thing with the right-hand rule is anytime you get a question on a test, you'll automatically notice that everybody's turning their arms all weird. That's okay. It's okay to look stupid as long as you can solve the problem. So in this case, this wire would be feeling an outward force from the board right in there between those two magnets. What I would like you guys to do is take a second, go ahead and try and solve. See if you can figure out what direction the force is going to be in this one based on the arrangement of the battery and the magnets. So go ahead, pause the video. We'll be back in just a few seconds to go over it. All right, hopefully we saw current is flowing the opposite direction here. So I is going to be going up. Magnetic field, in this case, is going to be going that way because we go from north to south. So that means I have magnetic field to the left. So right-hand rule, I go up, I go over, and now look at this. My thumb is pointing out, which means same idea. My force is going to be coming out of the page on this one. So when you flip the arrangement of both your magnetic field and your current, that's what you end up with. Now, how do we find out exact numbers for them? For a wire in a magnetic field, as long as it's perpendicular to the magnetic field, remember B represents magnetic field. As long as the wire and the magnetic field are perpendicular, meaning the current is also perpendicular to the wire, then it's just going to be current times the length of the wire times the magnetic field it's in. If it's not exactly perpendicular, then what you're going to do is multiply in a sine of the angle between them. And one thing to take into account here, B is measured in Tesla. Tesla is kind of a really large unit. Earth's magnetic field is around 5 times 10 to the negative 5 Tesla. So here we've got a problem. We've got magnetic field going to the right like this. We have a wire that's at a 60-degree angle to it with a current of 30 amps, and it's about 12 centimeters long. What I would like you to do is go ahead and solve for the force on that wire. Take a second, pause the video. We'll be back in just a second to go over it. All right, so when we take a look here, we're just going to plug in the values just as we see them on here. Current's 30 amps, length is 0.12 meters, sine of 90, and then we take 0.9 Tesla. When we multiply it all together, we get 2.8 newtons. Now, I found my force is going to be into the board. The way I did that was I is this way, B is that way. Where's my thumb pointing when I do that? It's going to be into the board. And therefore, this wire would feel a force pushing it this way when it's in that magnetic field. Now, let's try one last one. On this one here, I've got 100 meter of power line. 30 amps run through it just like in the last problem, but now it's perpendicular to Earth's magnetic field. I want to know what the force is. So go ahead, try another one, see if you can solve it. So just like I said a second ago, the magnetic field strength of Earth is 5 times 10 to the minus 5 Tesla. I plugged that in with my current and my distance, or length of the wire, and in this case I don't need to do anything with sine because sine of 90 is 1. So there we go. I just multiply by 1, I get 0.15 newtons, and that's all we've got on force on a current carrying wire.